Good afternoon, everyone. Welcome to the Grothendieck School. This is the second lecture on lower algebraic K theory of rings by Professor Amit Kuber in the K theory and totality series organized by the Grothendieck School. This is a continuation to our previous lecture. In this lecture, he's going to talk about excision as a tool for computing K0 and some other properties. Yeah, after you, Professor.
Thanks, Dipankar. So, yeah, just like last week, please, if you have enough bandwidth, then please turn on your videos. I would like to see you and talk to you. Yeah. Before we start, I mean, any questions from last week? Okay, they say that you had to wait for 7 seconds before you take answer as no. Yeah, so there are no questions, but of course you are welcome to ask questions at any point during this talk. Okay, so let's recall quickly what we did last time. So we looked at the overview of what K theory is all about, like it's a horizontal subject, and in particular we looked at this Grothendieck group, so-called Grothendieck group, which is defined for rings. And there are several steps of this construction, and we saw this 3-step construction, which I have written on the screen. Yeah, from rings, we restrict our attention to finitely generated projective modules to get symmetric monoidal categories. From there, we take the isomorphism classes of such modules, which is a set. And therefore, together with direct sum operation, we get the commutative monoid. And from a commutative monoid, we can get back to, we can get its group completion, which is an abelian group. Yeah, so this whole construction is known as K0. So associated to every ring, now we have a group. And if two rings are not isomorphic, if the Grothendieck groups of two rings are not isomorphic, then the rings are obviously not isomorphic. We'll see some more like a loosening of this statement today. However, if two Grothendieck groups are isomorphic, then we cannot conclude anything. Yeah, this is always a flaw in the system of classification. We associate to it an object, an invariant of a certain kind, and that if that invariant is invariants for two spaces happen to be same, then we cannot say anything. So we look for another invariant, which we are also going to do in the next lecture. But today, one more thing before we start, like for commutative rings in particular, we also have this tensor product operation. So therefore, direct sum and tensor product, they make it a symmetric monoidal category with a pairing, yeah, which is again a bifunctor which distributes over direct sum. And then from that, we don't just get a commutative monoid, but we get a semi-ring, commutative semi-ring, from which we get a commutative ring when we complete it, the underlying semi-group, the monoid. Okay, so this is what we have seen so far. And for K0, as examples, we saw two things, very simple, that K0 of a field and K0 of a division ring, yeah, is simply integers because we classify finitely generated projective modules by their dimensions. They are vector spaces. So simply by taking dimensions, we classify them. Well, is there anybody here who knows what a PID is? Yeah, can anybody answer that question?
It's an integral domain where all ideals are principal.
Very good. Integral domain where all ideals are principal. So if we start with a PID, then do you know any particular theorem? So it's called a structure theorem for finitely generated modules over a PID. So every such finitely generated module, what does it look like? You start with a module M, and what does it look like? Yeah. Anybody?
R mod A1 times R mod A2 and so on and so forth.
Yes. Okay. So it's a finite direct sum. Finite direct sum, correct? It's a finite direct sum of quotients. I mean, cyclic quotients of this. So everything is cyclic anyway. So ultimately, we can say that it looks like R to the power n. So these are the free quotients. like quotient by a unit, direct sum R mod, let's say P1 to the power R1 and P2 to the power, like these ideals, R2 and so on, where these are all prime or irreducible elements. Both are identical in this case, Rk. Okay, so this is what a finitely generated module looks like. Even if you have not seen module theory, you have seen this result in abelian groups, I hope. Yeah, for abelian groups, you have the same exact result. So this particular result tells us that all free modules, yeah, this implies that free over R is closed under submodules. Yeah, if it is just this and nothing else. Yes, Avar, do you want to say something? Okay. Okay, so free R is closed under submodules. Can you please mute yourself? If you don't have any questions, thanks. So a submodule of a free module is again a free module. And therefore, free R is same. Yeah, we have a stronger result in this case. Yeah, that free R is same as proj. Exactly. We don't just say that every direct summand of a free module is free. We are saying every submodule of free is free. So therefore, free R is same as proj, which means again we will get a kind of boring result, which is K0 of a PID is isomorphic to Z. Again, you look at what this number is, and this is invariant. Okay, so for PID is also a Grothendieck ring in this case because it's commutative. Another example is that of local rings. Yeah, local rings. A quick definition. I mean, I'm not only talking about first half ideal. Okay. In general, if ideas, then there is one very useful ideal, which is the intersection of all maximal ideas, which is called denoted by J for Jacob's of a ring. So this is given in terms of multiple ways. So it is intersection of all left ideals, left maximal ideals, which is also the intersection of right maximal ideals. Then it is also the set of all those elements of the rings which annihilate a simple module. Okay, so Sx is equal to 0 for all simple S. Then this is also the collection of all those x's in R which have a left inverse, yeah, such that said it wrong, has a left inverse.
Sir?
Yes.
Sir, is that for all simple S?
I'm pretty sure it's for all. Okay. Okay, perhaps I will tell you a bit later. I wanted to include that result for some other result. So 1 minus AX has a left inverse for all A in R. Write the same thing for a similar thing for right inverse. Let me switch on the fan. Okay, so this is the Jacobson radical, and the Jacobson radical in the case it coincides with the Jacobson radical, and the result that is very important here is Nakayama lemma. It says that for any module, if Mj is equal to, so which means the Jacobson radical always shrinks the module. I'm just giving you a sketch of the proof of what the projective modules are. So x1, x2 up to xk, they generate the module M if and only if the corresponding, so xi plus mj. So these cosets generate M mod mj. Okay, and one more result that we will need in this direction is that if you talk about the matrix rings, so matrix ring over this matrix rings, n cross n matrices over the Jacobson radical with entries from Jacobson radical are contained inside the Jacobson radical of the matrix ring. So these two results together will tell us that free modules and so these two results together will tell us that free modules over R and projective modules are exactly identical, because you start with a projective module P, then P direct sum Q is R to the power n. And in that case, what happens? You take a basis of P, a generating set of P, and you go modulo J. In this case, it's a unique two-sided maximal ideal. So R mod J is a field. It's a division ring. Particular result, this corollary will help you to like it will say that any two bases have exactly same number of elements. So now the size of that set is an invariant which you lift using this second start result. And this will tell you that free R is same as Proj R. And as a consequence, one more boring result, that K0 of a local ring is again isomorphic to integers. Okay, so far we haven't seen any very interesting results. Yeah. But we can talk about something interesting now. Yes, somebody wants to talk.
Yeah. Hi. Can you repeat how free R and Proj R is seen, like for this case?
Yeah, so you start with a generating set of a projective module P, then you also have its complement Q, some complement Q such that P direct sum Q is R to the power n.
Yeah.
Go modulo the Jacobson radical,
of
which
R.
means the unique maximal ideal. Local ring. Am I audible? Okay. So given, so what I was saying, that if you have a generating set for a finitely generated projective module, then when you pass on modulo J, then you simply get a vector space over the division ring.
Yeah.
And then any two different bases have exactly the same number of elements, and you lift using this. Okay. So another example, which now this example is quite interesting. So last time I think we discussed why we don't talk about infinite dimensional modules. Infinitely generated modules. Yeah. So for example, if you take R equal to the endomorphism ring of a field, infinite dimensional vector space over a field. Okay, then which means R is isomorphic to R direct sum R. This you can. What will happen that K0 of R will turn out to be 0. Essentially. So this is one, I mean, I still can't say it is a non-trivial example. Usually trivial means 0. Right? So, but we have only seen examples of integers. If the local ring happens to be non-commutative, then it was a Grothendieck group. Okay, so we need to now direct sum rings. I just want to say something about a property which is very important. It didn't really happen. This property. It's shortened as IBP. Yeah, so this IBP. So whenever R to the power m is isomorphic to R to the power n, then this implies that m is equal to n. Some rings which satisfy this on a commutative ring. If a ring R is commutative, then more generally, I mean, one very nice property that from a commutative ring to a field, you have a ring homomorphism. Yeah, there exists a ring homomorphism from a commutative ring to a field. Yeah, what do? You simply take R and assuming axiom of choice, you map it to R mod n for any maximal ideal m. So R mod m is a field, so you have a quotient map, which means you have a ring homomorphism, which takes 0 to 0, 1 to 1. Now, once you have this kind of map, then why does IBP hold? I mean, if you map M to this particular, I mean, in the case of commutative ring, so this is a field, let's say F. You take the tensor product and you, yeah, so this particular number is well defined. And for that reason, this IBP, more generally, even if you take a finite dimensional algebra, then that also has IBP. And why is IBP important in algebraic K theory in the first place? Because, yeah, so natural numbers to projective modules, yeah, proj are iso. You can send a map, say send a natural number to the class of R to the power n, right? This you understand what we are doing. So we are simply mapping n to the class of R to the power n. So this particular map is a map from, I mean, this is from the group completion, yeah, of n, which is completion of Projar ISO, which is K0R. And this particular map, so G of I, if and only if okay, so you can always see a copy of integers for PIDs for commutative local rings. Yeah, that was not a surprise. Or even local rings, because they also satisfy this property homomorphism to a field. So this is not a surprise. They should always contain, their Grothendieck groups should always contain Z because of IBP. Whereas at the top of this slide, you have an example where IBP isomorphic to R direct sum R, so you can't really do anything, and then you have this property. Okay, so a similar thing we can talk about actually. So let me. So in the category of rings, Z is the initial object. Z is the initial object in rings. Of Z to K0 of R. Sorry, I mistakenly wrote real numbers here. I didn't want to do that. So this is the corresponding K0 of unique. This particular map, so we use this particular map to define the reduced K0. Co-kernel of the induced map. So directly, this reduced K0. So in the case of IBP, you can see that Z is always going to be embedded inside K0 of R. So therefore, we don't want to talk about this trivial part. We quotient out by that. And then we only talk about this reduced K0. Okay. Any questions so far? Forgot to remind you that because Z is a PID, we have already completed this in Z itself. Okay, so now with algebraic number theory. Yeah, here we have to, I mean, again, I'm just going to give you a sketch of the proof, but that is dedicated. Okay, so if you have studied algebraic number theory, you might know several, like at least two equivalent definitions of Dedekind domain. The one that I'm going to use is this. It's in terms of the group of fractional ideals. So it's a commutative integral domain. Now this particular set, so this is, I'm just going that there exists an A in R such that such modules are called the fractional ideals. Yeah, I mean, this is the set of fractional ideals. Sorry. These are not just ideas. The ideals are contained inside fractional ideals. It's slightly larger. We are not looking at submodules of ring, but submodules of with respect to multiplication. I mean, let's give it a notation, frac of R. Frac R, then multiplication of ideals and the regular module RR itself. Yeah. So this is a monoid. This is always a monoid. Yeah, because you can multiply two ideals and R acts as the identity of this multiplication. However, we say that R is a Dedekind domain if this is actually a group with respect to this operation. Okay, so it's the reduced K0, it always has some trivial part hidden inside it. So those are the principal ideals. Yeah, where AI, where A is A is a, sorry, how should I technical details that when is this allowed to be? So unless a commutative integral domain, which is not a field, yes, fractional ideals. So principal fractional ideals, they are generated by just one element. Now these principal fractional ideals will always be there. You can't do anything about them. So if you quotient out, and they also form a subgroup. Whenever frac R is a group, then principal fractional ideals, they also interested in this quotient frac R modulo called class group of R. So class group of R is an important object of study in algebra, especially when you are talking about the rational numbers, which means algebraic number fields. So in this particular have to do does it have anything to do with K theory? Class group that perfect to Z direct some class group of R. Computations, then these are finite groups. Groups. If I start with K0 of this Z square root of minus root 5, direct some Z mod 2Z. So this is the first time you have seen a non-trivial example. Yeah. Example of this. Well, how does the proof of this go? First of all, you have to understand that you can prove this, that in a Dedekind domain, every ideal, it's very close to being a principal ideal domain in the sense that every ideal is generated by at most 2 elements. So here we have, these are principal ones, but the ones which generate this class group are the not be generated by one element. And in that case, if we are talking about this, the proof that I1 direct sum I2 is actually isomorphic to R direct sum projective modules, then they look like this. So finitely generated projective modules are all finite direct sums of fractional ideals. Fractional ideals, and for fractional ideals, we have this kind of simplification. Summands we take just one minus and then take the multiplication of the rest of them. Every P actually becomes isomorphic to R to the power K minus 1. Yeah, you repeat this process. I1 direct sum, I2 direct sum, IK. You repeat this process, and then ultimately you can write every finitely generated projective module as this form. And then you map the class of P and invariant the class of I inside CR, inside the class. And well, if you know a little bit of algebraic geometry and integral domain, the Zariski spectrum is connected. And therefore, you can define the rank of every module. And A happens to be the rank of this P, defined using localization. Yeah, so for domain, you localize it, you take the tensor product, and you take the dimension over the code. That number of this isomorphism. Yeah, you are simply mapping it to a number and an element of between algebraic number theory and K theory.
K-1.
Yes, it's K-1 because you also already have this I. If I turns out to be R, then you can pull it together.
Okay. No, I was asking that why is this getting increased by 1 when mapping? I mean, what is the intuition behind it?
Because of this first line. When you have I1 direct sum I2, then you get one copy of R and then I1 I2. It's sum of three things. Yeah, what will you do? First of all, I mean, you will also use R direct sum I1 I2 and then direct sum I3. This R and then you will get okay, so that's how it goes. For three terms long, yeah, you have to check the proof. These I are improper. These are okay. So now we should look at some K0 as a functor. Yeah, I feel like I'm rushing, but if you have questions, you should stop me. The functor, so K0 it preserves, or you can say it commutes with I mean finite direct sums of rings, which means I'm talking about products. Sorry, I should say finite and directed limits are preserved. So categorically speaking, directed limits are co-limits. Yeah, so direct limits is all about eventuality. Yeah, if something appears in some near future, then it continues to exist in some form. That's the idea of direct limit. This form. Whenever you have a sequence like this, direct elements in each of the objects in the diagram, universal property H such that whenever you have another object B with the same with a sequence of morphisms, then there exists a unique morphism from A infinity to B such that these triangles commute. Yeah, the ones which involve the map A infinity to B. All these triangles should commute. Or direct limit. And you can also have shapes other than natural numbers, but we don't need them. And that is of directed unions. So for example, yeah, I mean, I will give embedded inside M2R. Yeah, if you have a matrix of this size, then you can embed it as a matrix of in 2x2 matrices as this. So A mapping to A000. Then you can again go further and further and further. The directed union of this system is denoted MR. Yeah, note that we dropped N from MNR and we are just calling it MR, which have only finitely many non-zero entries. To be important for us, not just today, but also in the next lecture. This infinitary matrix group is very important. In a similar way, can you tell me how we can embed GL1R inside GL2R? Anybody?
Sending A to A001.
Exactly, exactly. Very good. So A matrix is still invertible. So we don't pad it with zeros, but we pad it with diagonal group that we'll get will be called the infinite general linear group. But again, only finite the diagonals are really a subset of MR. Yeah, MR under multiplication is a semi-group. Every matrix has a multiplicative inverse in particular. Okay, so these two, I'm not going to say anything more about this K0 as a directed limit, but I mean, why is it important? Because, oh, yeah, okay, I can say something about this particular part. So if you are given two rings and we are talking about K0 of R cross S, then this will turn out to be K0 of R cross K0 of S. Infinite direct sum and finite direct cross are the same over here. So which means now you have got the tools to compute Z mod mz for any non-zero m. Yeah, you can use the it as a direct sum of the direct product of rings. Yeah, where Z mod prime powers. And then you can use the same this result to compute this. Right. Similarly, if you are given a ring which can be expressed as a direct limit of its subrings, of a system of its subrings, yeah, so for computation purposes, this is actually really useful. So therefore, I mean, these are the functorial properties. If you actually look at this monoids to abelian groups, then that preserves all co-limits, not just these ones, but all co-limits, because it's a left adjoint to the inclusion functor. Yeah, so that's simply categorical. However, the way we came here, as I mentioned, this first one, yeah, that doesn't have any adjoint, so we just have this. All right. So if you are given a system, I mean, I did not talk about a system of directed system of rings and ring homomorphisms, then this is same as of this. This is what it looks like. So you can compute the individual Grothendieck rings and then take the direct limit. That should give you the same answer. Okay. So before we move to one important property which led to the discovery of higher K theory, for the Grothendieck group. So that is using idempotent matrices. Well, why idempotent matrices? So recall P belongs to Projar implies that there exists a Q such that P direct sum Q is R to the power n. Now, once we are talking about a direct sum, then obviously we will have a quotient map onto P. Let me call that pi, and then an inclusion from P to R to the power n. If I denote this particular, well, let's not. Perhaps I will use the letter F for this. So look at this map F. replaced with pi square. So it will be I pi. But if you use associativity over, so this is same as I come. Okay, so the map, the endomorphism f from r to the power n to r to the power n, in domain and codomain. So this endomorphism is an idempotent endomorphism. So it seems that so therefore idempotent endomorphism of r to the n with fixed basis, these should correspond to idempotent matrices. Correct? So if we fix a idempotent matrices. So now currently what is the problem here? A fixed basis. However, if I choose a different basis, then I will get a different. Right. So therefore, we have to talk about the action. So action of GLNR on idempotent matrices of size n on R by conjugation. Right. So identify it with let's say Q inverse AQ. Because actually, like, it just change of basis, but they actually correspond to the same projective module. We are just looking at it from a different perspective. So therefore, the orbits of this action are in one-to-one correspondence with projective modules. I mean, I shouldn't say projective modules. I should say direct summands of r to the power n. Is in one-to-one correspondence with direct summands of r to the power n. Now you have to simply take the, now you have to identify two different things. If like if you are just obtaining them by padding. So so what do we get? We'll get orbits of the action on idem R. Now here I'm not specifying anything, which means it's the infinitary matrices in one-to-one correspondence. Of course, I mean here when we are talking about two different n's and n and m, then you still have to make sure this all makes sense. Yeah, I mean I'm just giving you a sketch of this. Are in one-to-one correspondence with proj R iso. These orbits, you still have to convince yourself that even if you change the dimension to a next finite dimension, then and that way we get this particular set bijection. We can just having a set is not sufficient, right? We have to talk about an operation. So what is the corresponding operation? Well, if you have the class of A, class with respect to this operation, and the class of B, then we take their product. So A and B are actually identified with their finitary parts. Yeah, A and B are infinite matrices, but they only have finite non-zero off diagonal entries. So we take them in to be A00B B, and the class the product of these two classes is simply the class of this particular matrix. Like by the looks of it, this doesn't look to be a commutative operation, but it is. Yeah, so this is commutative and has identity. So why is it commutative? If A and B are, let's say, n and m size matrices, then actually you have this identity. So 0 IM 0 inverse, then A0 0 B. I'm just showing that the other matrix that you are interested in is B00A. That is conjugate to the conjugacy classes. So therefore, we have a perfect description monoid of isomorphism classes of projective modules. And therefore, we get this another description. So K0 of R is the group completion of the orbits of Idem-R by the action of GLR by conjugation.
What is the identity here?
So GLR was not padded by zeros, it was padded by ones. And so you have the identity.
This operation of which is defined on classes. What is the identity?
Zero. Zero, zero, zero. Sorry, am I missing? Yeah, zero is a matrix for which we don't need padding at all. Yeah, it's a zero.
So that is actually the image of the
identity. Sorry?
If you add zero in place of B, then it is the image of P.
No, it's not zero, it's identity. You have to add identity matrix of any order. There is the identity. The class of any identity matrix is the identity.
Okay.
An alternate presentation for this, which can be used to say something more about one more property, like about K0 as a functor. So K0 is Morita invariant. Okay, so if you don't know what this means, then I'm not going to give you an actual definition. The module categories of two rings are equivalent. Then there so the Grothendieck group, it shouldn't be a module category. It's just projective modules, finitely generated projective modules. However, how will you prove this? Well, you use this. You have to first see, for example, this mk over mnr is same as. Then a similar result you can also say for so GL. You can also conclude in a similar way that GL of R is the same as GL over MNR. Then idem of R is isomorphic to idem of MNR. Oh, wow, why am I talking about MNR? Yeah, that's not clear. So I want to say that R and MNR are always Morita equivalent. Identical. Their module categories are equivalent, and therefore their Grothendieck rings are also isomorphic. And I was showing a proof of this. Yeah, that you start by taking these baby steps and for GL and also for Idem, and therefore you will get that the actions are exactly the same. You can of course use the actual definition of Morita equivalence and then show this, but that only if you know what it is. Okay, so therefore you also know now what happens when you take, let's say, a PID and you take its authentic group is. Yeah, it's again Z. Okay, well, is a very powerful but an interesting theorem. This is Quillen-Suslin theorem. PID, yeah, then all finitely generated projective modules over Rx are free. I think you're right. Yeah, GLNR is same as right. Yeah. Let me just check.
How is
No,
GL
it's
different
right.
for
It's right. It's right. It's right. It's MNR. Yeah. Somebody was saying something.
No, I was asking when you were writing this GL. It is
No. This is GL of MNR itself. Yeah. Two big names associated with this theorem, that if R is a PID, then Proj Rx is same. Distinguish between them, you will again get Z. Okay, so of the study of K0, a very fast-paced study of K0, we will talk about a method of computation, and at the end of this, we will look at one example of a. I mean, we'll just state an example of a group is finite, non-zero. Yeah, we haven't seen any example like that so far. And usually, I mean, K0 is K0 or K1, K2, Kn. It behaves a lot like a homology theory. In homology is a long exact sequence. If you know certain terms, if you know, let's say it's a 3-term long exact sequence and you know 2 terms, then you know the third one. Up to some, you have some knowledge of the third term. I'm not saying exactly, but you have some knowledge of the third term. So we want our ultimate sequence consisting of K groups. But then the question is, how do we get that? So I should just give you some motivation from algebraic topology. Now, those who are not familiar with this, over here, I'm talking about singular homology computation of a topological space. You construct this C dot X. Yeah, this is the chain complex of generated by maps, continuous maps from delta. Yeah, I mean these continuous maps from standard simplices to X. All right. So is defined to be the homology of this particular chain complex. Homology is the failure of, it's the measure of failure of exactness at a particular nth entry. Now, in general, if you are given, if A is a subspace and A is nice, yeah, A is a subspace and A is nice, which means, well, means, or even otherwise, this particular result is still true, then to be the homology of this particular quotient the group CNA is a subgroup of CNX, so you take the quotient. Have C dot A, then C dot X, comma A, which is precisely this particular entry, and then this 0. So this is exact in the category of chain complexes. Well, what does this mean? That you can apply snake lemma a couple of times, very beautiful result in homological algebra or in general in mathematics, and you get a nice long exact sequence consisting of the homology groups. From here you get dimensions hn minus of a and dot dot dot. Over here you have hn plus 1 of x comma a, and these are the corresponding snake maps connecting morphisms, and you have a nice infinite long exact sequence obtained from this 3-term short exact sequence of chain complexes. This is nice because now suppose you know that this particular map is isomorphism and this is 0. If this is 0 and this is 0, then you know that these two are isomorphic. So locally you can do lots of computations. Yeah, so computations of homology groups is possible because of this nice long exact sequence, and this is also one of the existence of this long exact sequence is also one of the Eilenberg-Steenrod axioms for homology theory. Now, one more property is true. So this is called a relative homology group. Yeah. So we needed a third term. We knew something was happening with A, something was happening with X, but we needed a third term to complete this sequence, and that is the relative homology term. And one more property which is quite useful in computations is that of excision. So if U is a subset of A, subset of X, and U closure is contained inside A interior, then we can do something good, that Hn of X minus U, the pair, the relative pair X minus U comma A minus U, it has the same homology as that of the pair XA. Which means what's happening, that if you have this as U, this is A and this is X, then you can excise U out of both of them, and still the relative homology will not, the homology will not change. So this is very useful in computations. You have to remove some problem and get a beautiful result. Moreover, if A is a non-empty closed subset, which is a deformation retract of an open neighborhood in X, then Hn tilde of X comma A is also isomorphic. This is the reduced homology, which only changes at the 0th location. Also same as the quotient space of x by a. Yeah, so this is one result. This excision is also another property which is in Eilenberg-Steenrod axioms. This is also one of the axioms. The relative homology is obtained as the homology of the this reduced homology of the pair is the reduced homology of the quotient. Yeah, so again, one topologically speaking, you can simply treat A as one connected piece. Yeah, so this is also a very useful property for computations. So now coming back to algebraic K theory, yeah. So relative K0, we need to define relative K0. Our setup is going to be slightly different than this. We will be given an ideal, two-sided ideal of R. This is two-sided. And then because I includes inside R, we have a corresponding morphism from K of I to K0 of R. So we would like to have something at the last end. Sorry. I'm messing things up. I don't want to talk about this at the moment. I cannot say K0 of I add to K0 of R, there is a map, because I is an ideal which even though it is a subring of R, it doesn't have necessarily have unity. You understand? So therefore, I should in fact talk about this particular map, this Q map. So I will always have this corresponding map. So so K0 of R to K0 of R mod I. By functoriality, we have this K0 of Q. Yeah, from R to R mod I, we have a map of rings. And this map, we always know. Now we want to weave this together in a long exact sequence. But unlike this place, yeah, where A was given and X was given, and then X comma A was developed, the thing that we want will be placed here. Because we have a surjective map already, the relative K group will be placed here. Okay, so how do we construct this relative K group? For that, we have to look at double of R along I. Yeah, so this double of R along I is the notation for the subring DRI. It is a subring of R cross R such that the difference of these two elements lies in the ideal I. Like, very simply speaking, we actually have a pullback diagram in the category of rings. I mean, in the category of abelian groups, let's say for now. So this is the map which sends xy to x minus y. Then this is the, again, subring of R cross R. And this is to R, and this is inclusion. And this is pi1 minus pi2, where pi1 and pi2 are standard projections. This is a pullback. So double of R along I is this particular pullback. Okay, so what do we do with this? So there is one short exact sequence. Yeah, so this map is exact. Well, I have to describe what this map is. So this map is pi1. Because DRI is a subring of R cross I. So actually it is take the inclusion inside R cross R and then take the projection onto the first component. So that is the pi1. And this is minus I1, minus I2. Yes, minus I2, which means the second inclusion. It's inclusion in the second component but with a minus sign. So this particular map is exact, and so is this particular. This is an exact sequence in the category of abelian groups, and so is this one. And in fact, these two short exact sequences are also the same, essentially. I mean, not the same, but isomorphic. Here we'll take I1, and here we will obviously take pi2, and d of x comma y is defined to be x minus y comma x. So you can check for yourself that this diagram commutes. Okay, so, well, I'm doing lots of things and nobody's talking. So any questions? Yes.
Not a question, but
yeah,
not a question, but you should wrap up in some time.
Yes, I know, I'm aware. Yes, we have a question here. Okay. Fine. So dxy is x minus y comma x. Well, I will talk about this second exact sequence after some time. I'll come back to it, but for now, let's look at the first one. So we have this pi1 map, and so do we have pi2. Yeah, because dri is a subring of r cross r. From r cross r, you can go to r in pi1 and pi2 both ways. So the relative k group K0 of this pair r comma I is defined to be the kernel of K0 of pi2. Kernel of the map of K0 of dri, and this is K0 pi2 to K0 of r. So this particular, like if you take this, then you will get that this is a long exact sequence. This three-term sequence is a long exact sequence, which means the image of this is same as the kernel of this. See, we are not saying anything about this. Yeah, there is no zero padding here and zero initially here. In the next lecture, we will actually extend this three-term long exact sequence to a six-term long exact sequence where there will be three more terms here involving K1s. But three-term short exact sequence by taking this as the definition. And the corresponding excision property. Yeah, I mean, let me quickly remind you what this excision says, that the relative homology of the pair is same as the relative homology of the quotient, which means the difference between x and a, right? We are just talking about the difference. Here also we are saying, even in the more general excision property, we are also saying that only the homology is an invariant of the difference between the first component and the second component. If we cut out something from both ends, then it won't matter. Now, the same thing, if you look here, R and R mod I. Yeah, look at these two things. What is the difference between R and R mod I? Well, it is R quotiented by R mod I algebraically, which is simply I. So I is the difference between those two. And excision property says precisely that if at all we had a way of assigning to this ideal a Grothendieck group, then K0 of I would be K0 of R comma I. Okay. So I and like it only depends on the difference between R and R mod I. But what is the real meaning of K0 of I? We haven't ever defined that. However, we can. See, the important thing is that we have to associate to a ring its projective modules, finitely generated projective modules. Even if the ring doesn't necessarily have a unity, you can still associate to it its category of modules, out of which you can. So the module definition, if you remember, there is one, when we talk about the scalar multiplication from modules, then we say 1.m is equal to m. But we relax that condition. We don't take that condition if there is no 1. So by relaxing that condition, we still have the concept of a module, hence projective module, hence a finitely generated projective module, and you can do the entire process as it is. But let's be more careful and define it properly. So that we can do using Doro extension. So what is Doro extension? So given I, so I'm just going to write a functor and then you will understand what I'm doing. So all rings are contained inside, rings with unity are contained inside ring which possibly do not contain unity. Unity is identity. Yeah, identity can be abbreviated as I. So therefore, this is the category of RNGs. Yeah, they don't necessarily have I's. Yeah, that's why RNGs. So rings are contained inside these RNGs, but there is also this Doro extension functor, which is the so-called plus functor. This is inclusion, and this is the plus functor, which is the left adjoint to the inclusion functor. What does this plus construction do? So if I is a ring which doesn't necessarily have identity, and associate to it I plus, which is as an underlying group I direct some Z, together with multiplication. I mean, this is as an abelian group. And the multiplication is defined like this. So x comma n times y comma m is defined to be xy plus mx plus ny comma nm. So with respect to this, now this becomes a ring with unity where 0 comma 1, yeah, so I plus is a ring with unity with 0 comma 1 as the identity for this above mentioned multiplication. So every ring with unity can be universal, like in the best possible way. You can convert it into a ring with unity. And then you simply define, okay, and what happens if I is unital, I is already in rings, then I plus is isomorphic to the product of I and Z. Moreover, in general also, we have that the modules over I are same as modules over I plus. They don't really change much. And we define K0 of I to be the kernel of the map from K0 of I plus to K0 of Z. Wait. Yeah, K0 of I plus to K0 of Z. Because what is happening here, that we have this short exact sequence in the category of abelian groups or in the category of RNGs. So you have this map here, let's call it this map rho. So K0 of rho has a kernel. That kernel is defined to be K0 of I. You can check if I is actually a ring with unity, then this is simply a split map. This K0 of rho is a split map. So you will get back original K0 of I. Nothing changes over here. And therefore you can define K0 of a ring without unity also. And that K0 of ring without unity will turn out to be isomorphic to K0 of R comma I, the relative K0. So this is the excision property for K0. Right, so we have a short exact sequence, 3-term short exact sequence, and excision property holds. And well, in the next lecture, perhaps, so as an application of this, we will see that if I is the ideal MZ of the ring of integers, then K0 of I is without unity, which has a finite Grothendieck group. Okay, so with this, perhaps I should stop for today exactly 30. So I also kept a promise of finishing on time. So any questions?
So on the top line, the map, should it be K0 1?
No. You actually use the other map, which is not present. Actually, thanks for reminding me. Pi1 is already present here, so we use pi2 in that case. Wait. Oh, maybe you're right. I'll check in just a moment. Yes, it's pi1. It's pi1. Sorry. And yes, thanks, Yash. So why does excision hold? Because do this by replacing z. Yeah, I plus can be defined as I direct sum R as an abelian group, and the same kind of multiplication, everything works nicely. Here, instead of Z, you take R and you take K0 of rho and take its R isomorphic, and therefore K0 of I here and the kernel of K0 of pi1 and K0 of this, so they become identical. So that's also a reason why this holds. Yes. Any other questions?
Sir, what is the map from K0 R comma I to K0 R here in the second line?
K0 R comma I to K0 of R. Yes, that's a good question. So K0 of R comma I is a subgroup of K0 of dr comma I, from which you can map to K0 of R cross R, from which you can go to K0 of R. These three maps is this map. Is that okay?
Okay.
You can see that 1 comma 1, which is the identity in R cross R, that is also present here, because 1 minus 1 is the. Yes, I think somebody else had also unmuted themselves. Yes, Sudeep. Okay, I don't think we can hear you, Ardelin. Yes, Ardelin, just confirming that the previous question about Jacobson radicals should be for all simple modules, not for some. Yes, can look at the example. Yes. Okay, I was going to look at that, Ardelin. Thanks a lot. And if you can wait, we'll also talk for later. Yes, any other questions? Sudeep, you might want to write something, because we are not audible. If you have a question, you should write. Anybody else?
Yeah, hello.
Yes, Diksha.
Yes, sir, I have a question related to the isomorphism you stated in the previous page, I guess. GL of R is isomorphic to GL of Mn of R. Yes, this one. Sir, like in the right hand side, Mn R contains 0 by 0 matrix also, right?
Yes,
Mn
but that
R.
won't be an invertible matrix.
Yes. So,
even a single matrix won't be invertible.
Yeah, sir, what I was thinking, like GL of Mn of R, how you are defining, like Mn of R may contain 0.
Mn of R, you should treat it as block matrices. Okay, so Mn R, one element of this ring is a matrix, but you think of it as just one entry and then construct matrices.
Yes, so sir, what I was thinking is 0. Then what is the image in GL? Like GL is the direct limit, right? Direct limit of those GLNs.
It is the direct limit of GLNs of GL of MNRs.
Yes.
So take GLK of MNR. So the 0 matrix will not be in any GLK, so it won't be in the direct limit.
And
is that clear?
In the left hand side,
yes, it is also the direct limit of all GL and Rs.
Okay.
So the direct limit of all GL and Rs and direct limit of all GL KGM and Rs is isomorphic.
Okay.
These two direct limits are the same.
So, sir, how you are like identifying this as the isomorphism?
How I am identifying? I mean, for that, you first have to do this particular exercise. Yeah, you have to show that MK. This you understood, then do the same thing for GL.
Okay.
And then you take the direct limit on both sides. You will see why that is happening.
Okay.
You will just get different.
Okay.
Yeah. So instead of getting the sequence of 1 to up to 1, 2, 3, 4 here, you will get a sequence on this side of n and 3n and dot.
Okay, sir. Actually, I was thinking like GL of where you have written GL of R. I thought it is like GLN of R. Like GLN of R is isomorphic to GL of MN of R.
No. This is not GLN. This is the direct limit. On both sides, we are taking direct limits.
Okay. Okay, sir. I'll try to check, and if I have a doubt,
Yes. Check Rosenberg if you wish.
Okay.
Yeah.
Thank you, sir.
Yeah.
Sir.
Yes.
Sir, the continuation of this question. In this case, is the embedding R inside MNR as scalar matrices giving me the isomorphism after passing through the direct limit?
Yes, actually, I mean, I did not say that. I could have. I will write it over here. So a matrix A, I mean, let me use a capital letter A mapping to A000. You pad it appropriately. Yeah. So this particular matrix from let's see, R to MNR. Yeah. So, or you can think of it as a single entry to this. So according to this, in the category of RNGs, this will induce a Morita equivalence. So the category of modules is exactly the same. Maybe using some different language. Yes, Naba, can you speak again? Yeah.
Sir, I mean, I was suggesting that we can embed R into MNR via the scalar matrices, right?
Yes.
So I was guessing that whether that will give me, I mean, scalar matrices means A on the diagonal and other entries 0.
Oh no, we are not using that particular. You are trying to embed R in not as scalar matrices. Actually, just one non-zero entry. Because if you consider scalar matrices, then you have unnecessary non-zero entry, and then the rest are padded. Like this is the map.
Okay.
Something simpler. Yeah. Yes. I think Deepankar, we can stop the official session.
Yeah. If there are no other questions, then let us actually stop here. You can carry on the discussion if you wish.
Sure.
See you next week.
Thank you.